Okay, so today we will be discussing on antennas. So what happen when we consider antenna design at millimeter wave frequencies, what are the challenges we face, and then how to solve these challenges. So why we use antenna? So antenna, basically we can call it a transducer which will transform the guided wave into space wave. Now in free space, so the properties of electromagnetic wave, we know that the electric field, magnetic field and the direction of propagation, they form a right-handed orthogonal coordinate system, and electric field, magnetic field, they are also in same phase. So for antenna, we have to generate then these two electric field and magnetic field component which will be in same phase. So if I look at the different antennas already available or are being used at millimeter wave frequencies, this first category, it shows a parabolic reflector antenna. So where we use one feeding antenna, we call it feeder, it can be horn antenna or anything else, and then the electromagnetic wave is reflected by this parabolic reflector. So we use this for astronomy application where we need extremely high gain and very narrow beam width of the antenna. This is in the second example, it is showing antenna array. It is designed on laminates printed in printed circuit board technology. So you can identify one single rectangular patch. It is a type of resonating antenna, and in this particular example we have 1, 2, 3, 4, so 8 by 8 element array antennas designed for 60 gigahertz applications. And rightmost we have one dipole antenna, and it is designed on chip. So at 60 gigahertz already the wavelength is 5 millimeter, and when we are designing on PCB substrate, approximately we consider wavelength is lambda naught by root epsilon r. So antenna dimension, it becomes sometimes 1 millimeter or even less than that. There is a possibility to integrate an antenna on chip itself. So we will see some example. Sometimes even the packaging used for integrated circuit, that can be also used to incorporate the antenna structure. So when we do so, we of course face some problem. You can identify there are some cavities. So this particular antenna is designed in silicon substrate, and silicon, it actually we face problem of surface wave in silicon substrate. To avoid that, the people use some air cavity which is just below this antenna, which will improve the gain of the antenna. So for a resonating antenna, then it can, we can represent it by a series resonator or by a shunt resonator. In that resonator, we will be having one L component, one C component, and in addition to that we have one resistive component. So this resistance, it represents the loss inside the antenna structure and the radiation. So the radiation coming from antenna, we are representing by an equivalent resistor, we call it R rad, or the radiation resistance of the antenna. So as if it is a loss for the structure and it is coming out in the form of radiation. So R, that is equal to then R loss plus R rad. Now for a general antenna structures, we have to deal with many parameters. So how we define the characteristics of an antenna? There are several parameters. We should know the parameters first. So for example, the first important parameter is far field radiation pattern. So what we do? We just measure the electric field or power, which is square of electric field, its variation with respect to angle, and if we plot it in r theta phi coordinate, then the corresponding plot we call the radiation pattern. So here you can see a picture, it shows the radiation pattern of an antenna. So, the desired direction of radiation is shown by this arrow, and we call this is the main lobe of the antenna. In addition to main lobe, we can see we have some radiation in other direction also. So, these are called the side lobes of the antenna, and we have also some radiation just in the back side compared to the desired direction. We call it the back lobe of the antenna. And now, one more important quantity, that is the beam width of the antenna. So, we can define beam width in two ways: half power beam width and the first null beam width. So, how we define half power bandwidth? Let us say the gain of the antenna in the desired direction is given by x, then we come down by 3 dB, and then the corresponding angular separation, it is known as the half power beam width of the antenna. It is an important parameter for antenna for scanning purpose, because it defines the resolution of any antenna or two objects when they are separated and we want to see them as separated two different objects. So, the separation it should be more than the half power beam width of the antenna. We can define it in another way, that first null beam width. So, if I consider this particular direction, we do not have any radiation in this direction, we call this is this antenna has a radiation null in this direction. So, first null left hand side to first null on right hand side, the angular separation we call the first null beam width of the antenna, and usually for most of the antennas half power beam width is half of that of the first null beam width of the antenna. Next, another important parameter is radiation intensity. So, how we define it? Power radiated from an antenna per unit solid angle in a given direction. So, in my desired direction, obviously radiation intensity will be higher. Other direction, radiation intensity should be as small as possible. Third parameter is directivity. The ratio of the radiation intensity in a given direction from the antenna to the radiation intensity averaged over all direction is called the directivity of the antenna. We can also define it in another way: ratio of the radiation intensity in a given direction over that of an isotropic source or isotropic radiator. One isotropic radiator, if it does not have any loss, ideally it radiates power in each and every direction. Next, we consider another parameter, gain. When we define directivity of the antenna, we did not consider any loss inside the antenna structure, but in practice we have to face this loss. So, if we want to incorporate this loss in directivity definition, so we have to use this definition we call gain of the antenna. This is defined as 4 pi into radiation intensity divided by the total input accepted power. Now, in usually gain definition, it does not consider the loss due to input reflection. Whenever we feed any antenna, at the feeding port, obviously there will be some input reflection loss due to the impedance mismatch between the guiding structure and the antenna input impedance. So, if we want to also incorporate this input reflection loss, because if there is any input reflection loss, that power is going back to the source and it is not being accepted by the antenna. Sometimes we define one more parameter, realized gain or absolute gain of the antenna, and in that case we also incorporate what is the input reflection loss in calculation. Next, another important parameter is polarization. So, basically by polarization we means what is the direction of the electric field. It can be in a straight line, in that case we call it linear polarization. It can be circular polarization, elliptic polarization, and now till now we are discussing about the radiation characteristics of the antenna. From input impedance point of view, there is one more definition of antenna bandwidth. We call it impedance bandwidth of the antenna. So, by impedance bandwidth, then we can understand how much power antenna will be accepted over which range of frequency. Now, impedance bandwidth, it can be defined in many ways. So, for impedance bandwidth, what we do? We plot S11 or the input reflection coefficient of the antenna versus frequency. So, let us take one example. If I plot frequency, let us say in gigahertz versus S11, which is in decibel scale. If S11 in dB is 0 dB, that means whatever power I am feeding to antenna, it is being reflected back, 100% power is being reflected back to source. Now, if the antenna accepts power, then we have some negative value of S11. So, let us say we have measured the S11 or we have simulated the antenna structure, from that we have a knowledge on S11, and when we plot it, it looks like this. So, this is we call the midband frequency of the antenna, where it accepts maximum power. And now, we can define the impedance bandwidth in many ways. In some definition, mostly for handheld devices and small antennas, we consider 10 dB matching point. So, we will see where these values, the value of S11 is minus 10 dB, then the corresponding bandwidth delta f, we call it sometimes 10 dB bandwidth. So, over this bandwidth, if I calculate what is the reflection coefficient at this point, and from that what is the power being accepted by the antenna. So, approximately 90% power is being accepted by the antenna if I consider S11 is minus 10 dB. But in some application, a more stringent definition is used. In that case, they do not want even this 10% loss. So, we further decrease it to another level, let us say minus 15 dB. We call it minus 15 dB bandwidth of the antenna, and if I convert this minus 15 dB to input power loss due to reflection, it comes approximately 5%. So, over this band, then we can say that at least 95% power is being accepted by the antenna port. So, with this definition, now let us see what are the problems we faced at millimeter wave frequencies. At millimeter wave frequencies, if we want to design any antenna on printed circuit board or laminates, then the losses, what are the sources of losses, already we know, and this loss increases with frequency. So, do you remember the three sources of losses? The first one is dielectric loss, second one conductor loss, and third one loss due to surface wave generation. And this third component, surface wave loss, it also increases significantly at millimeter wave frequencies. So, all of this power lost to these three reasons, due to these three reasons, they are not being radiated by antenna. So, it is a total loss or wastage of my power. So, we have to avoid this loss somehow, and we will see what are the solutions and what are the methods people use to minimize this loss. So, first one already we know, at millimeter wave frequencies, for example, for a microstrip line, the conductor loss is given by this, which we already learned, at it increases with frequency. Dielectric loss, it is also a function of frequency, it also increases at millimeter wave frequencies. Next important point comes choice of a substrate. What should be the dielectric constant of the substrate? What should be the tan delta of the substrate? What should be the thickness of the substrate? So, coupling with substrate modes, or in other words we also call surface wave, it is insignificant only if the thickness is less than 0.01 lambda naught. Otherwise, we have to consider the effect of the surface wave mode. Now, if I consider a frequency 60 gigahertz, lambda already 5 millimeter. So, 0.01 lambda naught it is too small, too thin. Most of the substrate will be more than this, and we can't avoid the effect of surface wave generation. Antenna efficiency, considering the effect of surface wave, it can be given by eta equal to 1 minus square root of epsilon r minus 1 into h by lambda, where h it represents the thickness of the substrate, and you see it is a function of h by lambda. So, thickness with respect to the wavelength or operating frequency, and one more term, one more epsilon r term is here. Now, if I plot eta versus epsilon r for a given thickness, let us say h is fixed and frequency is also fixed, that means lambda is fixed. In that case, eta it decreases with epsilon r. Why antenna efficiency decreases with increasing dielectric constant? Because when we increase the dielectric constant, it generates more surface wave, because the thickness of that substrate is fixed, but in terms of lambda, it is effective thickness, it is increasing with increasing epsilon r. So, for one typical example, a patch antenna designed at 60 gigahertz on a substrate with the same thickness, but in two different substrates with different epsilon r. When we design it on a 58880 substrate, where a dielectric constant is approximately 2.23 at 60 gigahertz, the antenna efficiency it comes 60%, and it reduced to 25% when the same antenna is designed on alumina substrate, which has higher dielectric constant epsilon r equal to 9.5. So, what do we expect then? If we use higher epsilon r, antenna efficiency will decrease. So, the conclusion is that when we go for millimeter wave design, we have to use lower epsilon r as well as smaller thickness. Next, I am going to show you some studies which will which can be used as the guidelines whenever we are going for antenna design at millimeter wave frequencies. Here, what I am going to show some results obtained for two different types of antenna. The first one is printed dipole, which is one example of balanced antenna, and the second one is printed patch antenna. So, both of these antennas they are printed on laminates using printed circuit board technology. Now, in this plot we are going to show the resonant length versus substrate thickness variation. So, before this study, let me discuss a few points on printed dipole, how it radiates, and the printed patch, how it radiates, and what are their basic characteristics, because both of them are resonating antennas. At the fundamental resonance frequency, their length will be lambda g by 2, but they represent two different groups. Dipole antenna is an example of balanced antenna, and printed patch antenna, it is an example of unbalanced antenna. So, if you look at this equivalent circuit for printed dipole and printed patch, both are resonating antennas, but in the equivalent circuit, printed dipole is represented by a series resonator, where this capital R it includes both the radiation resistance and the loss in the antenna structure itself, whereas for the printed patch it is a parallel resonator and R represents same things. Now, how we determine that printed dipole? It should be represented by a series resonator and printed patch by a parallel resonator. So, what we do? We can simply calculate the input impedance, or if calculation is too complex, we can use any full wave simulator or electromagnetic simulator to simulate the structure, and that is how we will be having the input impedance, and then we plot the imaginary part of input impedance. At resonance frequency it should be 0, and now at below resonance frequency, if it is negative, that means below resonance frequency input impedance is capacitive, and above resonance frequency input impedance is inductive. So, for a series resonator, we know that below resonance frequency it is capacitive and above resonance frequency it is inductive. So, that is why for a dipole antenna, the equivalent circuit we can determine that it should be one series resonator. Similarly, for any unknown antenna structure, we can plot the input impedance. It's looking at the imaginary part variation, we can determine what should be the equivalent circuit. It should be one series resonator or parallel resonator. Now, if I look at the electric field plot of any resonating dipole antenna, it looks like this. So, the length of this antenna is lambda g by 2 at resonating frequencies, and if you look at the electric field, it is maxima on the central plane, and we have in the far field radiation, electric field is parallel to the wire or this line of this dipole antenna. We have linear polarization, and this dipole it radiates its maximum radiation in the broadside direction, and we have radiation null along the wire. And now, look at the electric field plot for a rectangular patch antenna. For a rectangular patch, it radiates from its fringing field. Okay, let me discuss a little more on this fringing field, how it radiates. Let me start from a very basic resonator. Let us say we have a microstrip line resonator of length lambda g by 2, obviously at the resonance frequency. Now, both of these two ends, they are open circuited. So, at resonance frequency, if I plot electric field along the line, then we will be having maximum leftmost and rightmost edges, and if I plot current distribution, so this is the plot of electric field, and if I plot the current distribution, it will have just opposite variation. It will be having maxima on the central line and 0 since the ends are open circuited. Now, if I want to fit this resonator at this edge, we see that electric field is maxima. So, corresponding potential difference, it will be also maximum between the strip and the ground plane, but current having minimum value. So, the impedance seen by the feed line, if I connect it here, it will be infinite. Now, on the central plane, we have current maxima and electric field minima. So, if I feed at this point, we are expecting input impedance is 0. For microwave circuit, mostly we use 50 ohm system. So, for impedance matching, then the feed point will be somewhere in between this z equal to infinity and z equal to 0 plane, and the thumb rule is that you consider 1/3 length from left hand side. So, if the length is L of this resonator, then we have to consider approximate length from left hand side is L by 3. This resonator, when its width is very small, it will not radiate, but if we keep on increasing the width of the resonator, it starts radiating, and this radiation comes from the fringing field at these two sides. So, if I look at the fringing fields plot, so this is the direction of electric field. I did not show it in this diagram. So, since it is radiating, so if left, this is in left hand side, if it is in upward, so here it will be downwards, and at the end we have fringing field. So, now how we have radiation from the fringing field? Obviously, some of this component, it has to be for that electric field and magnetic field, it has to be in same phase. So, let us say this is the fringing field components. So, I am drawing the side view. At bottom we have the ground plane, and this is the top plane strip. Now, I can represent the fringing field along two orthogonal axes. So, in that case we see that these two electric field component, let us say this is 1, this is 2, they are in same direction looking from broad side, and we will be having we will be having maximum radiation intensity in broad side direction from these two fields. So, to increase the radiation, what we have to do? We have to increase the width of this resonator, and that is how we obtain a rectangular patch resonator. So, now look at this electric field plot. We have fringing field left hand side and right hand side. So, it represents the length of this antenna in this direction. Now, this length, it should be lambda g by 2 at the resonating frequency, and we will be having maximum radiation intensity in the broad side direction of this antenna. Next, we will see resonating length of the antenna, it is a function of frequency. Not only that, it also depends on epsilon r of the substrate. Why? Because of this fringing field components. For different epsilon r, we will be having different fringing field components. So, we have different length correction factor because of that. So, we will take a break, then we will start again. Thank you.